I wanted to do a more interesting example of a proof by induction. It's a trickier example, and oftentimes you'll see me do these examples and you'll say, how did you come up with that proof? And I'll just say that practice makes perfect. So let's prove that for all n greater than or equal to 0, n cubed minus n is divisible by 3. Okay, so that means that for all integers n greater than or equal to 0, you look at this quantity, n cubed minus n, and it's always evenly divisible by 3. Okay, so with any proof by induction, we first write a predicate. P of n is going to be n cubed minus n is divisible by 3. We're still at the stage where whenever we write the predicate, it corresponds exactly to what we want to prove. You'll see that will, hopefully in the near future, that will change. So the next step is to do the base case. That's P of 0. And as usual, the base case is pretty easy. We have 0 cubed minus 0, that equals 0. And 0 is indeed evenly divisible by 3 because 0 divided by 3 is 0. Now we need to prove that for all n, P of n implies P of n plus 1. And this would complete the proof if we can prove that. So step 1 is to assume P of n is true. Think of n as some large number. And now we need to conclude that P of n plus 1 is true. So what is P of n plus 1? This is what we need to prove. It's that n plus 1 cubed minus n plus 1 is divisible by 3. So this is what we need to prove, and we can assume that P of n is true, so we can use that as a fact. Okay, so I'm going to move this up here and keep working. So let's expand out n plus 1 cubed. This is equal to n plus 1 times n plus 1 squared. This is equal, and n plus 1 squared, so this is equal to n plus 1 times, now we have this n plus 1 squared, that's equal to n squared plus 2n plus 1. And now we have to multiply these together. So we get, so distributing the n here, we'll get n cubed plus 2n squared plus n. And then distributing the 1, we'll get plus n squared plus 2n plus 1. And this equals n cubed plus 3n squared plus 3n plus 1. Now if you're having trouble kind of expanding out these algebraic expressions, then you really need to practice them. It's something I'm going to assume that people are okay with and that they've seen in high school and certainly in calculus. Okay, so we just expanded out n plus 1 cubed. This implies that n plus 1 cubed minus n plus 1 is equal to this quantity minus n minus 1. So that's going to be equal to n cubed plus 3n squared. I'm going to subtract an n here, so that's plus 2n, and then I have to subtract a 1. So here you are in the middle of a proof, and you're trying to prove that this particular quantity is divisible by 3. What is P of n again? We've sort of forgotten about it. We assume that P of n is true. What is P of n? P of n says that n cubed minus n is divisible by 3. This is a cubed up there. So we have this expression. We're trying to prove it's divisible by 3. And what we know is that n cubed minus n is divisible by 3. But somehow we have to use that fact. In this expression down here, I don't see n cubed minus n. I see n cubed plus 3n squared plus 2n. So I'm just going to change it a little bit. This is equal to n cubed minus n plus 3n squared plus, now I'm going to add that, I subtracted n, I'm going to add it back, 3n. So see what I did here? I took this expression and I subtracted n and then I added n. So that's totally legal. Okay, and now we have an expression here that's more useful for us. So P of n implies that this quantity is divisible by 3. And here we can write this as 3 times n squared plus n. And this is certainly divisible by, this term is certainly divisible by 3. That's because there's a 3 sitting out here. So we've taken one term that's divisible by 3, and we've added another term that's divisible by 3. Okay, so since this is divisible by 3, it means that we can write it as 3 times k for some integer k. Okay, but that means that this entire quantity is equal to 3 times k for some integer k plus 3 times n squared plus n. Which means that this is equal to 3 times k for some k plus n squared plus n. And now you can see that this original expression here, which was n plus 1 cubed minus n plus 1, is equal to 3 times some integer, and so therefore 3 divides this quantity evenly. So what we've shown, we started from n plus 1 cubed minus n plus 1, and we showed that it's actually equal to 3 times some integer. So therefore 3 divides n plus 1 cubed minus n plus 1. But that's exactly what we wanted to prove for Pn plus 1. We wanted to prove that n plus 1 cubed minus n plus 1 is divisible by 3. That's what we did. So we showed that P of n implies P of n plus 1. Now where exactly did we use the inductive hypothesis? Right here. Because we had n cubed minus n, and our inductive hypothesis is that P of n is true. So it's divisible by 3, so we can write it as 3 times k. Then we had this other term here that, by luck, there was a 3 sitting out in front, so it was divisible by 3. So when you add them up, you get that the whole quantity is equal to 3 times some integer. So the entire quantity is divisible by 3.